A single question, 3 words. Can machines think? Alan Turing didn't know the answer, neither did anyone else. But someone had finally asked it out loud. In the beginning, AI was not a technology. It was a bet. A bet placed by a small group of mathematicians who believed, against all evidence, that human intelligence could be written down, formalized, reproduced. In 1956, John McCarthy gathered the world's brightest minds at Dartmouth College for a summer of optimism. They gave this field a name: artificial intelligence. They expected to crack it within a decade. They did not crack it within a decade. But they kept going. In 1966, a program called ELIZA appeared. A simple script that mimicked a therapist. People confessed secrets to it. They knew it wasn't real. They confessed anyway. Then came the reckoning. In 1969, Minsky and Papert proved mathematically that neural networks, the most promising approach at the time, couldn't solve basic problems. Funding vanished. Labs closed. The first dream was over. The promises had outrun the math. The first winter had arrived. For 20 years, AI was a punchline, but a handful of researchers refused to stop. They worked in obscurity, unfunded, largely unpublished, often laughed at. One of them was Geoffrey Hinton. In 1986, Hinton and his colleagues revived neural networks using a technique called backpropagation, a way for machines to learn from their own mistakes. Nobody paid much attention. In 1997, IBM's Deep Blue defeated Garry Kasparov at chess. The world's most celebrated game fell to a machine. People called it a trick, a brute force calculation, not real intelligence. Then, in 2006, Hinton announced something he called deep learning. Layers upon layers of neural processing trained on vast amounts of data. Again, almost no one listened. Then, Watson beat the 2 greatest Jeopardy champions in history on live television. Language understanding had entered the room. The data was piling up. The hardware was catching up. In 2012, a team at the University of Toronto submitted a neural network called AlexNet to the ImageNet Visual Recognition Competition. They didn't just win, they won by a margin so large it rewrote the rules. In 2016, DeepMind's AlphaGo defeated Lee Sedol at Go, a game so complex, so intuitive, that experts believed no machine could master it for decades. Then one paper changed everything. 8 authors, 8 pages. A new architecture called the Transformer. Published in 2017 under the title "Attention is All You Need." Every large language model you've ever used, GPT, Claude, Gemini, runs on this. In 2020, GPT-3 proved that language itself could be predicted, and that prediction, at scale, looks a lot like understanding. In late 2022, ChatGPT launched. 1 million users in 5 days. The public realized this is real, and it's moving fast. The curve was no longer rising, it was taking off. What happened next has no historical parallel. In 2023, GPT-4 and Claude demonstrated genuine multi-step reasoning. Not just completion, judgment. The gap between AI and human performance on complex tasks began to close in real time. By 2024, AI agents could navigate the web, write and run code, make decisions across long chains of tasks, without being asked step by step. In 2025, reasoning models arrived. Systems that don't just respond, they think first. They pause, consider, revise. Chain of thought made real. 4 years. More progress than the previous 70 combined. 80 years of AI history fit on this timeline. From a single question in 1950 to systems that reason, act, and build in the span of one human lifetime. The next 80 years will not fit anywhere. We're at the beginning of something that has no name yet. Pay attention. Cortexscale. Big questions, clearly answered. Your brain runs on about 20 watts. It learned your name, your mother's face, and how to catch a ball long before you could explain any of it. The system we're comparing it to was trained on an almost unimaginable amount of text and data. So this is not a fair fight. That is exactly what makes it interesting. Let's start with the numbers. The human brain contains around 86 billion neurons, and on the order of 100 trillion synaptic connections. A frontier AI model can have on the order of trillions of parameters. Silicon is obviously faster at raw arithmetic. Modern AI hardware can perform staggering numbers of operations every second, while neurons fire much more slowly. But slow does not mean simple. Biological neurons are rich, messy, adaptive components, and researchers have shown that even approximating a single neuron can take surprisingly complex artificial networks. So round 1 is basically a draw. Now the really wild number. Your brain is doing all of this on roughly 20 watts, about the power of a dim light bulb. By contrast, training a top-tier AI model can consume enormous amounts of electricity. And even routine AI use is far more energy-hungry than human thought. That does not mean the brain is better at everything. It means biology is unbelievably efficient. Evolution produced a system that can learn continuously, run in real time, and stay adaptable, all on the energy budget of a small household bulb. So if this round is about efficiency, the brain takes it easily. This is where the gap gets really strange. Show a small child a dog once or twice, and they usually start generalizing almost immediately. AI systems usually need far more examples and far more compute to build that same flexibility. And by the age of 3, a child has already learned language basics, faces, movement, physical intuition, and social cues from a relatively tiny slice of lived experience. That is one of the brain's biggest advantages. It does not just absorb patterns, it learns how to learn from the world itself. So round 3 goes to the brain. Now we switch categories, because this is where silicon hits back hard. Ask a person to multiply 3,847 by 9,213 in their head. Then ask a machine. That is not a close race. For arithmetic, search, retrieval, repetition, and large-scale cross-referencing, AI wins by a landslide. A human brain is powerful, but it is one brain. It gets tired. it loses focus. It cannot clone itself on demand. So on speed, precision, and scale, this round goes clearly to AI. This may be the most important part of the whole comparison. Not how each one succeeds, but how each one breaks. Human thinking is full of bias. Misread probability, remember things incorrectly, and often feel certain when we should not. AI fails differently. It can hallucinate, follow patterns without real understanding, break on edge cases, and confidently produce answers that sound right but are simply false. And because it sounds fluent, that failure can be dangerously persuasive. So the key point is not that one fails and the other does not. It is that they fail in different ways. Humans struggle with consistency and bias. AI struggles with grounding and common sense. That makes this round a draw, but also a very revealing one. AI was originally inspired by the brain, but modern systems are not digital brains. They borrowed the metaphor, then went in their own direction. And on the other side, brain-computer interfaces are real, but they are still sampling a tiny fraction of what the brain is doing. We are nowhere near reading a whole mind in any complete sense. So the real convergence is not that the two become the same thing. It is that each covers weaknesses in the other. AI is fast, tireless, and scalable. The brain is efficient, embodied, flexible, and grounded in the real world. They do not replace each other cleanly. They complement each other. Hundreds of millions of years of evolution produced something that runs on 20 watts, learns from very little, and can reflect on its own existence. A few decades of computer engineering produced something that can process huge amounts of information at incredible speed. So the question was never, which one is better? The better question is what happens when human judgment and machine scale start working together well. That is the real story. And honestly, we are only at the beginning of it.